In this problem, we have the following circuit. We're asked what is the frequency in megahertz of the high frequency pole for the amplifier shown. Now, although we're asked for high frequency, we're also going to be looking at low frequency and the midband voltage if we wanted to find those. But first, we're going to do our problem. So our problem here, we have high frequency, and there's a few things about capacitors that we should note. So a capacitor at low frequency, that means that we are going to have an open circuit. And then a capacitor at high frequency, we're going to have a short circuit. The way I remember it is that capacitors at low, it's LO, and I tie the O here with O for the open circuit, and I write that out. So low is open, and then the capacitor at high is just short, and that's just because it's the only other thing it could be. Now inductors, just for knowledge, if an inductor is at low, it's going to be a short, and if inductor is high, it's going to be an open. So they're inverse of each other. But right here we only have a capacitor. So for a high frequency, we are going to be dealing with a high, meaning that we have a short. So if we have a short circuit, that means that our wire is just going to go from here to here as if we don't have a capacitance. So our current is just going to flow through here. And that means we're going to have the same thing across here also. And so that means all of our current is going to go through here, a path of least resistance. And that means we're going to have no voltage across our output. And so this is all that we have to look at here because of this short circuit. So when we write it, we're going to use the formula that we have right here. We're just going to be replacing some of the values because it's for a slightly different problem. So we are going to have our high frequency be equal to 1 over 2 times pi. And this is just to convert it into the radians form that we look at instead of the angles degrees. And then we have 1 over our capacitor. Now, what capacitor is it since we have 2? Well, the capacitor is the one that is affecting it. We can see that this has no effect. We can pretend that it doesn't even exist because the current flows through here. It's just like a normal wire. Well, this capacitor, if we were to think of it as a normal wire, it changes from a capacitor to a normal wire, and this affects this voltage. Because if it was at low, it would change. It would be open and the current would flow into here because we wouldn't have a wire here. And I meant to kind of connect these to show it's like a real wire, just like almost no resistance. And so that means through here we are going to have the CI, and then inside of here it's being multiplied by our resistor in parallel. So we are going to have our RI times our RS. So inside of here we are going to have our RI in parallel with our RL, and then this is just going to be closed off, and we would convert this to the parallel form, which is just RI times RL, and this is over RI plus RL. And then we would just plug in our values. I did this in Symbol Lab, just like this. And so with that, we are going to get a pretty large number. This number is going to be about 101,77097, and then we'll just have a decimal, and this is in hertz. Now we want this in megahertz, so we're going to convert this. We're going to do 1 mega over 10 to the 6, and then we're going to move the decimal place 6 places to the left. And that means our answer is going to be approximately 10.1771, and that's the answer for our high frequency. Now if we wanted our low frequency, we know that we would have an open circuit. Remember the low, we have open. And so with our low frequency, we're going to have open circuit. That means that this is going to not have a wire here, and it's just going to stop right here. So no current makes its way past this into the output. And so that means our capacitor here is this CS. And if we were to use Thevenin's equivalent, which is how we found this, we would zero out this, and we would see that our resistor here are in parallel. That's how we found this parallel right here. And then if we were to zero it out like this, we didn't have this, it's an open circuit, they would be in series. So we would add them together because resistors in series, we just add. And that's it for the low frequency. Now for the midband voltage gain, it's going to be slightly different. For the midband voltage, we have correct here, our V out over Vs, that's going to be just H of S. And then we have our RL, which is really going to be our RI in this problem because it's the resistor that our output voltage is over. And then we have divided by Ri plus our Rs, which is the source. And then we're not done here though, because we need to look and see that we have everything to the right of this that we need to take care of. So this is being multiplied by the current flowing through here. We are going to have our GM times our VI, and the VI here is we're just going to write GM here because we have the current flow through here, and then we have our resistors that are in parallel right here and give us the output voltage. So we are going to just have the resistors in parallel formula, R0 in parallel with our RL, and then we would just plug in our values, and that will give us the answer for the midband. But that is the answer for this problem and how we would look at different scenarios for it.